Thank you very much all for coming here. I'm super happy to be here and talk about some of my research. So I'm based at the Institute for Physics and Astronomy here in Aarhus, and I work in a group called Science at Home. Our mission is essentially to bring science to the people. So we don't want to just kind of make science a thing for scientists or for people working at the university, but we want to reach out to people. And we have essentially built this machinery that turns people's pastime, so games and fun, into real, tangible scientific research. I'll talk about one of our main projects, which was employing around 200,000 players to help to build a quantum computer, which is kind of the field that I work in. So to get started, let's talk a little bit about quantum computation. And because that's a bit of a hard thing, I'll take a step back and first talk about normal computation. So computing is essentially information processing, which means that we have to deal with information and processing. And when you kind of really boil down these things to the basics, information has a lot to do with bits. So that's how you store information in a computer. Bits are these things which are 0 or 1, and all information can be encoded in these long strings of zeros and ones. But it doesn't help just to get this encoding, we need to do something with that. So we need logical gates. These are the things that kind of tell how to combine these zeros and ones bits together so that we get stuff happening. And quantum computation works in exactly the same way. We have quantum bits and we have quantum logical gates. But quantum bits are a bit different from normal bits. So normal bit is a 0 or a 1. Quantum bits can be kind of both at the same time, and that's kind of the weird property of quantum systems. And it means that we can really start kind of building these massive systems for storing information, because these quantum bits can be in multiple states at the same time. It essentially allows us to build these parallel computers by using quantum bits. This means that computational time can actually really go down exponentially. So if we were to have a quantum computer with 260 quantum bits, we could already do computations that with a normal computer would take longer than the life of the universe. So if there's anyone here who's kind of struggled with I don't know, clogging their hard drive with too much information or trying to run a calculation which is taking like days or weeks or months, you can kind of appreciate how nice it is to be able to speed up things. So yeah, so this is a thing that would be very nice to have. And in Aarhus, we're kind of working towards this. I say we, I actually don't, I'm a theoretical physicist, but our experimentalists are setting up a lab where we can trap atoms. So we have an architecture for a quantum computer where one quantum bit is encoded into a single atom. And there's a way of trapping single atoms into essentially kind of like an egg tray that's made of light. We call it an optical lattice, where we can kind of put one single atom in each well in the egg tray. And in this way, it's possible, and it's been done already, to trap up to 200, 300 atoms. So this could be the very kind of basis for a quantum computer that has around that amount of quantum bits. And I just said that, 260 would already be a really good number to have. So that's kind of a really interesting architecture to work with. The problem with this architecture is that the logical gates that I mentioned that we need for processing the information, they're a bit harder to implement. So kind of storing the quantum bits, easy enough. Logical gates, it's a bit more tricky. And what is especially tricky about this is, so first kind of the way that we do logical bits is to take one of these atoms, one quantum bit, and transfer it over to another one. We let it collision in a very controlled way, and then we can kind of take it back. And this is how the processing is done in this architecture. Moving these atoms around it's actually quite difficult. It can be done, but what's really hard about it is doing this in an optimal way. So we want to do it quickly and we want to do it precisely. We need precision so that we don't have any errors in our calculations. And we need speed so that we can run this in a proper way. And the very hard thing about this is that speed and precision, they're kind of complementary to each other. So when you move something really fast, you kind of tend to lose the stability of an atom. And likewise, if you want to move it in a very stable way, it takes a lot of time. So there's kind of a trade-off between these two things. And then there's a whole lot of things which has to do with the fact that we're dealing with atoms, which are quantum things, and they're quite slippery and tricky to deal with. So there's actually a whole field in quantum information processing called quantum optimal control, which deals with these problems. So at first, we basically took the state-of-the-art algorithms from this field, and we kind of pushed this problem through these algorithms. And we got solutions to the atomic transport problem that were, they were really precise, but they were a bit slow. And we couldn't figure out how we can get the algorithm to speed up this process. So what we did was a bit more unusual. We kind of presented this problem to another kind of supercomputer, which is the human brain. So we turned this whole problem into a game. This is what the game looks like. It's called Quantum Moves, and if you kind of look at the game interface, you might recognize that almost as a kind of cross-section of this egg tray that I was talking about. So you see these two wells that trap atoms. And the purple liquid, kind of behind just the controller, that's an atom. That's actually, we run this whole thing on a very precise quantum physics engine, so when you play the game, you're actually solving a quantum physics problem, which is pretty cool. And what you see here is that the atom is actually kind of a liquidy thing, and that's a very accurate description of what an atom is. Atoms are not like the little balls that I was kind of representing in the previous slide. But basically, we can turn this whole problem of how to move atoms into a game. We released it. There have been different versions out, and to date, around 200,000 people have played this game over 6 million times. And every time someone plays the game, we have one solution to the problem of how to move the atom. And when we start looking through these solutions, we actually find that some of them are extremely, extremely good. People are able to find extremely fast solutions. They're not necessarily the most precise solutions, but they're fast. And when we take these really fast solutions and then we feed them into these state-of-the-art algorithms, we start really getting somewhere. So we basically find that when we combine these kind of human ideas, human notions on how we can do quick transport with really the brute force machines, algorithms that can kind of perfect this human stuff, we get results which are fast and precise.